If someone shows you a healthcare AI model with 95% accuracy, your first reaction should not be, "Ooh, that's very impressive." Instead, it should be 95% of what exactly? In healthcare, accuracy is one of the most misleading metric we use, and I'll explain in the next few minutes why. Let's begin with something obvious and something really basic. What is accuracy? In a nutshell, accuracy tells you the proportion of decisions that have been correctly made. So, of all the decisions that you make, what proportion do you make that are correct? So, if all the decisions that you have made are correct, if you make 100 decisions and all of them are correct, your accuracy would be 100%. If you make every other decision correct, then your accuracy would be 50%. So, that's what it is in a nutshell. Now, intuitively, this is very objective, it's very straightforward, it looks very simple. The more decisions that you correctly make, the higher the accuracy. It looks great on paper. This is a metric that's used the most commonly, and you will find it in papers, in white papers, in blog posts, in the press. And on its own, accuracy as a metric is not the problem. The problem is that accuracy answers the wrong question. So let's break the intuition behind accuracy, because this is where it really fails in healthcare. Imagine a situation where you have a disease, the prevalence of which is low, say 1%, and you are tasked with developing an algorithm which can identify anyone who has that disease. You can come up with a very naive and simple algorithm which says that everybody who comes in for test, they don't have a disease. And guess what? That algorithm on its own will be right 99% of the time. In other words, the accuracy of such a model would be 99%, but it would be completely useless. So in this particular case, accuracy rewards laziness. So if you just have a lazy algorithm which says nobody has a disease, the accuracy that you get would be really high, to 99%, which is great on paper. So this is one situation where we can clearly see that accuracy is problematic. If you have a very class imbalanced situation, say where you have a disease which has a very low prevalence, then accuracy alone as a metric is not going to be a great metric. Further, another problem is something to do with error asymmetry. What I mean by this is, if you make a wrong decision, which is, say for example, you suspect somebody to have cancer. Now, if you make a wrong decision and they end up not having cancer, but you suspected they have cancer, so this would be a false positive. And the repercussions of this is that the person in question would end up having some additional tests. Now let's look at the flip side. Imagine somebody actually has cancer, but your algorithm suggests that this is low risk or they don't have cancer. Now this is a case of false negative. So the repercussions of this would be much severe, because now we have a situation where somebody might end up having a serious condition, but you failed to identify it early enough. So we can clearly see an error asymmetry here, where one type of error is not as problematic as making a different type of error. So clinically, errors that you make, there is a difference. However, accuracy as a metric will treat all kinds of errors the same. But clinicians, they clearly don't consider all kinds of errors the same. Third point is about harm visibility. And what I mean by this is that accuracy obviously rewards making overall correct decisions, but if there are minorities or those small number of people who might end up really getting harmed with wrong decisions, those kind of situations would be completely masked, because you have this algorithm that has a very high accuracy, and then those minorities or those very small group but very high risk groups, they're completely masked. So let's look at how we calculate accuracy. So accuracy in a nutshell, as I said, is the number of correct decisions. So you can have two types of correct decisions if we are looking at in the two-class problem. Somebody has a disease and you correctly identify they have a disease, so that would be true positive. Or somebody who don't have a disease and you can correctly identify that they don't have a disease, so that would be true negative. So true positive plus true negative divided by all the decisions you make. So that would be again true positive plus true negative plus false positive plus false negative. And here in this formula, you can clearly see that the numerator, so the higher the numerator overall in relation to the denominator, the higher the accuracy. Both true positive and true negative, they equally contribute. And that is the problem so clinically we have already established different types of errors have different repercussions. So clinically they are not seen equally, or they are not considered the same, but accuracy on its own metric, it would consider all kinds of decisions, correct decisions, wrong decisions, they would all be treated equally. So all true correct decisions treated equally, all wrong decisions treated equally. So let me give you one simple example of why this really matters clinically. Imagine at a population level, you have an algorithm where you want to screen people. So you want to identify high risk people, and there's a disease that you suspect that many people might have. So you do a screening, population level screening, and say there is an algorithm that gives a very high accuracy, 85%, 90%, whatever, a very high number. The problem is it might actually miss the very patients that you want to identify, those high risk patients, that small proportion of patients. So you can still have a very high accuracy AI model. What would happen is it will give false reassurances to even those people who might actually have a disease, but this high accuracy algorithm is just giving them false reassurances. And it simply means that it's clinically dangerous despite the high accuracy. So the way to approach an AI algorithm is to stop focusing only on how often it makes correct decisions, but in addition, you need to start thinking about where does it make wrong decisions, what kind of subgroups are affected, and who pays the price when you make those wrong decisions. And that way of thinking would naturally lead you to start looking into things like prevalence, false negatives, the threshold that you should be using, and subgroups. Not as technical details, but as clinical concerns. So the next time you see an AI model claiming high accuracy in healthcare, just pause and ask 3 questions. 1. What's the prevalence in this population? 2. What errors does the model make, and whom do they affect? 3. What metric actually reflects clinical risk here? If those questions aren't answered, accuracy on its own tells you very little.